Welcome to episode 16, Automatic Control. Most of today's cars have a cruise control. If you have slowed for traffic and want to get back to highway speed, you just push a button. The car comes back to highway speed by itself. The cruise control creates a speed error signal by subtracting the actual speed from the goal speed. This error signal changes the amount of fuel injected and the amount of air being allowed into the engine. Finally, the car's speed changes. Here is our simplified, one-block cruise control model ready to run. Our one account is preset to a car speed of 0. Signal builder speed goal for model time 0 is 0. It changes to speed 5 at time 5, and changes back to speed 0 at time 20. Here are the graphs. Trace 1 is the goal over time. Trace 3 is the value on the account, the actual car speed at any model time. Once the goal changes from 0 to 5, the car speed account takes about 3 time units to follow it up to 5. The account then takes the same amount of time to follow the goal back down to 0. The middle trace is curious looking at first glance, but we can reason out why it looks like it does. Each error transient begins with the full value of the error so that corrective value is pumped into the account at maximum rate. When the speed error is half corrected, say at time 6 and 21, the error and correction rate can be half. A more realistic cruise control model has 2 accounts in a row. If I am the car speed error calculator, I don't get to command acceleration directly. I communicate with the components that eventually get acceleration changed. These include the gas pedal, which takes time to change. Once it has been changed, fuel and air flows begin to change. Eventually there is different acceleration and thus a speed change over time. We will lump all our delays for changing acceleration into one account. Our 2 account outputs are then acceleration, followed by speed. What can go wrong? We should only suffer a bit more delay, one would think. Here are the graphs. We have complete craziness. The car oscillates itself to pieces. The average of the desired car speed can still be seen as the center line of each section of sine wave, but no one would get in this car. What do we do? First, we should agree on what we have created. We can trace around our familiar oscillator circuit from episode 13, finding 2 accounts and an inverter. We have the path required for oscillation. Have we ever seen any trick that discourages oscillation? Yes. In episode 14, we learned about shock absorbers that convert a car's bounce energy to heat and get it out of the model. Eventually the car settles back to the correct elevation above the wheels for its weight. How did we model the shock absorber? We took the output signal from the first account, the one making velocity from acceleration, and brought it back to our force summing point at the start of the chain. We made sure this signal had a sign that would reduce force as a function of velocity. This shock absorber idea came from our earlier idea of air resistance, introduced in the Skydiver episode. There, too, we took velocity in air and changed it to a drag force, getting energy out of the model. For our shock absorber and air resistance models, we used the 2 account chain of acceleration to velocity, then velocity to displacement. Our cruise control chain moves the model earlier by 1 step in the motion process. Now acceleration to velocity is our second account, our second system delay. And earning acceleration by getting fuel and air rates changed is our first account, first delay. But limiting oscillation is a matter of math, not the specific application, so the oscillation killing signal, or energy loss signal, is still made from the output of the first account. Here is our two-account cruise control model with the new, and hopefully curative path. The two accounts. The original goal generator. A sum point for the feedback coming from both account 2, our car speed, and account 1, our car acceleration level. The feedback paths have gain blocks that we can turn on or off, up or down for system tuning. We will start with account 2's feedback path at gain 1, and account 1's feedback path also at gain 1. Sheet 1. Things have calmed down. At time 15 we can see a settled car speed. Same at about time point 30. It looks like we should try tuning our middle account feedback gain. For the best car ride in episode 14, we said that 1.5 bounces might be good after the car hits a pothole. What would be our best ride equivalent here? A responsive cruise control that doesn't keep hunting, that hits a sweet spot between craziness and laziness. Let's try a gain of 0.5. Here it is with a gain of 2. Here it is with a gain of 4. Let's show them all together. 4 is clearly too sedated. 2 is marginally sedated. 1 has a little overshoot. 0.5 has a ton of overshoot. I think 1 is best for now. Vectors provide an easy shorthand for talking about sine wave phase and signal size. A vector's angle corresponds to a sine wave's degree of delay with respect to another sine wave. Here we highlight a delay sequence from episode 13, showing the corresponding vector representations of each delay. A vector's length represents sine wave amplitude with respect to some original amplitude standard. Let's reason out what is curative about feedback from the first account output, with some easy vectors. We create oscillation by having phase delays of 0 to 90 degrees across the first account, then 90 to 180 across the second account. With the first account feedback path off, only the 180 signal is inverted, becoming 0, and driving the 0 phase point at the start of the chain, with the 0 phase signal from the far end of the chain sustains oscillation. We are telling the first account exactly what it wants to hear. With the first account feedback path back on, we sum equal amounts of 90 and 180, and get a vector of 135 degrees. We invert this and it becomes 315 degrees. 315 applied to the point in the chain that expects 0 or 360 is very frustrating to an oscillator. It causes the loss of a big percent of signal amplitude each cycle. Soon there is nothing to see. When we crank up the percent of 90-degree signal with respect to 180-degree signal, the inverted vector sum gets even worse for oscillation, as we saw when we tried a higher value for curative feedback. We now have our first tool for discouraging oscillation, a tool based on ideas from previous episodes. But we need one more version of this idea. Let's return to our single account control circuit and drive it with sine wave, not a step function schedule from Signal Builder. We remember that when we tried to get the output of the account to follow our stepped goal signal, there was a delay of 3 time units in the waveform. Now let's see this delay in terms of sine wave phase. Trace 1 is our drive for this follower arrangement, its goal. The account output, trace 3, follows the drive by around 45 degrees. This corresponds to the 3 time units of delay from when we were just using steps. But look at the middle signal, the input to the account, which is the follower error signal. It is a sine wave also. What does its phase have to be? We remember from episode 13 that a single account processing sine wave always gives us 90 degrees of sine wave delay across the account. That makes the signal at the input to the account around 45 degrees ahead of the sine generator. What does this mean? It means we have a second version of a phase look-ahead oscillation limiting tool that doesn't require us to tap into the middle of an account chain. That's good, because in some real-world systems, it may be impossible to hang a sensor in this part of a mechanism. Think of the stock market behavior model. What if account 1 is investor sentiment? No investor is going to tell you what move he or she intends to make before their trade is a done deal in public record. Let's insert our new tool into our 2-account control system and tune it as before. There can still be 2 adjustments, one in the path of the raw second account signal and one for the previewed path. In this version, we did not draw in the amp for the 180 signal, as we will only be tuning the preview signal. An amp you don't include is just a gain of 1 on that signal line. Once again, we will choose the best-looking last account signal from a variety of look-ahead gains. Here is a look-ahead gain of 1. Now 0.5. Now 2. And now 4. Here they are together. Of these choices, let's use 2. Our homebrewed look-ahead circuit has a pre-packaged version in the model component library. It is called the PID module. The PID is compact and convenient, and our models in episodes 17 and 18 use them. Let's get to know it by putting the PID into our cruise control model and tuning it for good performance. It makes a much cleaner model, one block instead of several. This will help, as our episode 17 and 18 setup screens are pretty full. The PID setting box has 3 adjustments. Proportional is just basic, unconditioned, in-phase feedback from the end of the account chain being controlled. The proportional level of the error. The setting they call derivation is their version of our middle-of-the-follower-derived preview signal. As we turn up derivation gain, we bring the net loop delay from 360 degrees, which oscillation loves, down towards the low 300s, which oscillation hates. The setting called integral we will leave at 0. It is for systems that have long-term drift issues that we don't have. We give the PID a proportional setting of 1 and start our tuning with a derivation value of 1. Then we try 0.5. Then 2. And then 4. Now we show them all together. Once again, we have to pick something between craziness and laziness. For a spunky enough response, we may have to accept a bit of overshoot. 1 looks good. We are ready to start controlling models. We have 2 controlled models left to show in this series of videos: watershed management and landing the rocket. Can you think of interesting ways to use automatic control in some of the earlier episodes? Scilab is software buy-in for the world's community. Help them with dollars, publicity, and contribute code. TTS Voice is copyrighted 2014 and licensed by LinguaTech, GmbH. Visit them at linguatech.de. Text and graphics copyrighted 2019 by William Rhodes Design.